this video, I want to do an example problem looking at three-dimensional rigid body kinetics, along with using some simplification based on the symmetry of the object that we're looking at. So, in the example, we have a three-dimensional object. It's a cube, three-dimensional cube, which is balanced on a fixed point at one corner with a support structure in the middle, and the cube can rotate around this support structure. The blue section is supposed to be vertical. The drawing's not perfectly vertical, but it can rotate about that support structure, and it's hollow, so each of the sides is made up of a thin plate. And the problem statement basically is that we want to understand if we were to apply a force at one corner located out here where the green circle is, into or out of the screen, and apply a force of 50 newtons for 1.2 seconds, if we know that or can observe that this structure takes 5 seconds for the cube to complete one revolution, which gives us a measure of its angular velocity. What is the mass of the structure? So there's a few things going on here, and we'll kind of walk through some of the considerations that we're going to have to make to make this solvable. And the first thing we're going to specify is that we need a coordinate system. And so the coordinate system I've drawn on here, this XYZ coordinate system, has axes located at the center of gravity of the mass of the object, and each of the axes passes through the planes of these sides. So normal to the side on the kind of top here, the back, and this front left side. So the first step to kind of figuring this out would be to determine our appropriate mass moment of inertia. So we need to kind of pick an axis for this, and I'm going to start by picking the x-axis as the axis that I want to take this mass moment of inertia around. Now the reason I'm picking the x-axis is that because of symmetry, so the object has symmetry in all three directions, we can actually compute the mass moment of inertia about any axis that passes through the centroid, and it'll be the same then for all axes that pass through the centroid. So we have some advantages there of the symmetry that we can make use of. So I'm going to start by computing Ix, and because this is a hollow cube, it's probably easiest to look at it from the perspective of each individual thin square plate that makes up the sides. So there's kind of two things going on here. We have two sides that are normal to x, meaning x passes through this top side and also passes through the bottom side. The drawing may not make it look that way, but that's just because I can't draw. Then we have four sides, here, here, and the two on the back, that are more like parallel to the axis x. So we can look up either in a textbook or other places to find some equations, or of course we could compute them, but I'm not going to do that here. And what we can find is that for a thin square plate with one of these sides that are perpendicular to x, we would get, let's call this 1, we would get 1/6 ma squared. Now I do need a little bit of clarification because this m is not the m we're solving for down here, which is the mass of the whole thing together. This m would be just one of the sides, so I'm just going to put a bar on top of that to indicate that it's only the mass of one of these sides. So this contributes the mass moment of inertia from two of my sides. Now I need the mass moment of inertia of the other four, and again I can look up in a textbook and I can find an equation. The one that I found basically says that for a side like this, where we're rotating around an axis parallel to that side, we would get 1/12 ma squared. Now the difference here being that we are not rotating around an axis, in this case that passes through the side, but instead is at a distance away from it, 1/2 of a side length. Our side length here is A, so now I need to add on to this a parallel axis theorem term, which is m times the distance, 1/2 A squared. So I got 1/12 ma squared and 1/2 a squared m. So if I add these two together, I get take 1/4 a squared. 1/12 plus 1/4 is 1/3. So I get 1/3 m a squared. Now, the net total contribution to this is 2 times this first one, because we said that corresponds to 2 of my sides, and 4 times my second one, which is here. So if I add 2 times this and 4 times this, I get 1/3 plus 4/3, so I get 5/3 m a squared. All right, so I've got this now, the mass moment of inertia in terms of the side lengths. However, we also said that we wanted to find eventually m, so it would be useful to convert this equation to m. We know that m is 1/6 of the overall mass because the cube is made up of 6 sides. So if I substitute that in, then I get an Ix of 5/18 ma squared. So that's the mass moment of inertia that I want to use for the overall device. And again, because of the symmetry that I have, I can say that this is equal to the I that I need for rotation around this blue vertical axis. Okay, so now that we have the mass moment of inertia, we can actually start evaluating the kinetics of the situation. So because we have a force being applied for a period of time, it would make the most sense to use the impulse momentum method for solving this problem, because a force applied over a time is an impulse that we add to the system. So to do that, we need to think about what we're adding into the system. We're adding a force being applied over here at some distance from the rotation center. So actually we're adding a torque. And rotational impulse, angular momentum is of the form T1 to T2 mdt, where m is that force at a distance, or the torque that we're applying. So that gets realized as the force multiplied by the distance. Now the distance I haven't really mentioned here, but I've got it described on my drawing as this distance b, which is basically the distance from the centroid to the location of, from the center of the cube to the location where the force is being applied. And therefore we can multiply force times distance to get torque, and then we need to multiply that by time, and that basically captures everything in here. So if that force is constant over that time, then we can pull that out of the integral, and we basically just have change in time. This is then equal to the angular momentum, and we start from rest and go to some new angular momentum, so therefore there's no change in angular momentum there, and that basically completes the equation. Angular momentum is equal to I omega, and we just said what I was 5 over 18 m a squared omega. Ma squared for I, and then omega being added on. So we've got most everything we need, and we just need to kind of plug in what we know and what we don't know. So starting with the force is 50 newtons. B, B by geometry is equal to root 2/3 times the side length. So we can look that up, and that means we're going to multiply here square root 2 over 3 times 1.5. And the time over which the force is applied is the 1.2 seconds. All right, so I've got everything on the left-hand side of my equation here. Now I need to set this equal to the right-hand side. 5 over 18 m is what we're solving for. A is 1.5. And omega is related to then how fast the cube ends up spinning as a result. So we said previously that the time it takes to complete one revolution is 5 seconds. So we need, that means we have one revolution per 5 seconds. This needs to be in radians per second. So we'll say omega is 2 pi, which is one revolution, in radians over 5 seconds. And now we have an equation with basically everything in terms of numbers except for the mass that we're ultimately trying to solve for. So we can go ahead and rewrite this in terms of mass, and we get 18 over 5 times root 2/3 times 1.5 times 50 times 1.2. I think I got everything from there. I got that multiplied across. Now I need to divide by 1.5 squared times 2 pi over 5. And if we do all of that correctly, I think we get 93.6 kilograms. So putting this all together, we've managed to calculate the moment of inertia, again, taking advantage of the symmetry of the object and some provided equations that we can look up. And then we've applied the principle of impulse and momentum in order to say we have a force applied over a time. That force actually gets realized as a torque, and we set that equal to the angular momentum, I omega, and then plug all of our various quantities in order to solve for that. All right, so I hope that was helpful. Thank you very much.